This video has to do with the 30, 60, 90 degree triangle proof in geometry. And so I just want to kind of explain how we came up with the 30, 60, 90 degree triangle and the proof that makes the relationship between the side lengths work. And so when we talk about an equilateral triangle to begin with, we know on an equilateral triangle all our side lengths are the same. So I'm just going to pick some side lengths here. I'm going to say that all of our side lengths are 8. And another unique thing about an equilateral triangle is all the angle measurements are the same. So not only are the side lengths the same, our angle measurements measure 60 degrees. So I'm going to go ahead and label these two angles here to be 60. I'm not going to label this angle up here in the middle, up here at the top vertex. And then I'm going to do this. If I was to take a line and let it come straight down from the top vertex of the equilateral triangle, and if I was to let that swing, you would notice that if it just stopped swinging straight up and down, it would develop a perpendicular line. And of course that perpendicular line would have a 90 degree angle, and which means we've also bisected this angle up on the top, which now becomes a 30 degree angle on each side. There's another thing that's unique here. If we drop this line straight down from the top vertex, we've also bisected the line segment at the bottom of the equilateral triangle, which means now that this has to be 4 on each side of the dotted line. And then of course Pythagoras figured, well, we could figure out the length of the dotted line or the other leg by just using the Pythagorean theorem. So if we did that, we would have a squared plus b squared equals c squared. And if I plug some numbers in here, I have a squared plus 4 squared equals 8 squared. And if I keep going, I have a squared plus 16. All of this equals 64. If I subtract 16 from both sides, I'm getting this. I'm getting a squared equals 48. And if I take the square root of that, a is going to be the square root of 48. But instead of changing that to a decimal, I'm going to go ahead and put that in what we call reduced radical form. And so I'm thinking, well, that could be a equals the square root of 16, that's my perfect square root, times the square root of 3. And of course, the square root of 16 is 4 times the square root of 3. So this dotted line has to be 4 times the square root of 3. And Pythagoras noticed a relationship, and so did other mathematicians, with the 30, 60, 90 degree triangle, and it is this. When you look at your hypotenuse, the leg opposite the 30 degree angle, or the smaller of the two legs, is always that relationship of half the hypotenuse. So my hypotenuse is 8, the leg opposite the 30 degree angle is half of that, 4. And then we notice that the taller of the two legs, or the leg opposite the 60 degree angle, always has that 4 as the coefficient of the square root of 3. So it's going to be 4 times the square root of 3. If I was to sit there and try some other side lengths here, and so I'm just going to go ahead and erase just the side lengths and just pick some other side lengths and see how that affects our 30, 60, 90 degree triangle. And I'm going to erase the Pythagorean theorem here. And let's just pick some side lengths, and this time I think I'm going to pick 4. So I'm saying all my sides are 4. Well, then that means that this side opposite the 30 degree angle has to be half the hypotenuse, so this would be 2 and 2. And I'm going to plug these numbers into the Pythagorean theorem, so I have a squared plus b squared equals c squared, and so a squared plus 2 squared equals 4 squared. So a squared plus 4 equals 16. I have a squared, I'm going to take a little bit of a shortcut here, equals 12, because if I subtract 4 from each side. And so instead of taking the square root of 12 to get a all by itself, I'm going to put this in what we call reduced radical form. So a is going to equal the square root of 4 times the square root of 3, because 4 times 3 is 12. Well, the square root of 4 is 2 times the square root of 3. And once again, there's that relationship that we're looking for the taller of the two legs, or the leg opposite the 60 degree angle. It's always the side length of the shorter leg times the square root of 3. And that holds true for every 30, 60, 90 degree triangle. So if we're going to do that, let's just go ahead and do some examples on the worksheet here. And so when I look at this right here, problem number 1, I notice that this is the hypotenuse, so the leg opposite the 30-degree angle has to be half of that, which is 4. And of course, my taller leg, or the leg opposite the 60-degree angle, I'm going to label that 60, has to be this number times the square root of 3. So 4 times the square root of 3. I'm going to go ahead and do problem number 2. I noticed that the smaller the legs, or the leg opposite the 30-degree angle, is already labeled to be 24. So that means the hypotenuse has to be 48. And of course, this number times the square root of 3, so 24 times the square root of 3 would be the other missing side. When I get to problem number 4, it's a little bit harder here, because problem number 4, they give me the leg opposite the 60-degree angle, and remember, this is always times the square root of 3. Well, I don't even have times the square root of 3 here. So instead of having 7 times the square root of 3, I would say, well, then this side must be 7 and this must be 14. But wait a second, the square root of 3 is missing here. The only thing that is left is 7. So I'm thinking, okay, well, if I had to multiply by the square root of 3, what would be the opposite of multiplying by the square root of 3? Well, that would be dividing by the square root of 3. So this side must be 7 divided by the square root of 3. And of course, remember, this side is always double. So if I took 7 divided by the square root of 3, and I doubled that, multiplied by 2 over 1, I would get 14 over the square root of 3. So this side right here must be 14 times the square root of 3. I hope that makes sense. Let's try another one like that. Problem number 5. Let's see, problem 5, wait a second. They give me the leg opposite the 30-degree angle. So I know that this must be double. So 27 times 2 would be 54. And of course, what is my leg opposite the 60-degree angle? Well, it's always this number times the square root of 3. So 27 times the square root of 3. Hopefully this will help you do all assignments involving the 30, 60, 90 degree triangle.